So far, in the time that we've spent together talking about the electrical effect, it's been so very theoretical, very physics sort of a vibe. These fundamental particles exert forces on each other, and they also create invisible electric fields associated with the energy of electrical interactions. And I mentioned along the way that at some point the whole thing would turn very practical, because as everyone knows, what has happened is that the human race has put the electrical effect to great practical purpose. We rely on electrical technologies to not only advance, but at this point, support our civilization. And so that's what's going to happen today. I'm going to start talking about things sort of abstractly and theoretically, and start talking about them in a more practical, more engineering way. But the conversation starts with a quantity that I've already defined, and that is the voltage. So I start with a slide that is familiar because it's very much, it might be exactly the same as it was in a previous presentation. When the electric potential, that is the energy per charge, is different at two locations in space, we say that there is a voltage. Now, calculating the potential difference is just acknowledging that there's a difference and subtracting, and that is measured in volts. Of course it's joules per coulomb in a theoretical physics sort of a sense, but now we're going to start to refer to that potential difference as a voltage, where 1 volt is a joule per coulomb. Voltage is the push that makes charges move. In order to really establish that idea, I leaned heavily into the analogy between potential difference and the flow of water under the influence of gravity. And I'm going to continue to push my luck with that analogy as far as it'll go, because the flow of water is something tangible that I can visualize based on experiences from my everyday life, where the electrical effects, even when I'm talking about them practically, remain invisible. And so once again, I need to create some difference in energy per unit charge in space. And there are 3 distinct ways that the human race has figured out how to create practical voltage. Now, it's true, if I blow up a latex balloon and rub it on my head, I can stick it to a wall, and there's energy associated with the charge on the balloon. The trouble is, it's not much energy, and it's not really practical to get static electricity, not moving deposited electrons, off of an object to do practical things. So static electricity doesn't appear on my practical list, but of course, batteries do. There's a lot of detailed chemistry that we're not going to get into. Suffice it to say that inside every battery, whether it be the battery inside of your cell phone, which is remarkably small for the amount of hours that it can make your cell phone run, or the batteries that are inside your calculator, or the battery that is inside of an automobile, or the enormous batteries that are inside of a submarine, allowing it to run silent under the ocean for long periods of time. There's always a chemical reaction inside of the battery. Battery potential difference, battery voltage, is all about a chemical reaction that precedes and separates charge. As we know, that doesn't last forever. It's possible that we learned in chemistry class that many chemical reactions only go one way and cannot be made to go in reverse. Irreversible chemical reactions. And in the simplest forms of batteries, that's the case. The chemical reaction proceeds, separating charge in the battery and creating a potential difference until the chemical reaction wears out, until there's simply no more reactants and it's all products. Your cell phone, however, creates a battery of has within it, a battery of very particular chemical reaction, the lithium-ion battery. And that chemical reaction proceeds, separating charge. But when it's exhausted, that reaction can be forced to go in the opposite direction. It's not a 100% sort of situation, and eventually cell phone batteries are scientifically, chemically exhausted and can't be recharged. But to a limited extent, that reaction can be pushed in reverse, so it could be reset and run again. Because of the availability of that chemistry and how we've organized it into small boxes and packages to produce potential difference, that's one of the three major sources of potential difference, major sources of voltage. Another is solar. Some of you may be losing focus during the lesson, might look out the window and see that on the roof of this building there's a large collection of solar panels. It was discovered quite a while ago, in fact, that there are materials that when light impinges upon them, that the molecules and atoms in that substance can have their electrons ejected by the energy that the light brings. This is called the photovoltaic effect. It's not the last time that we'll talk about it, but that's the operating principle of solar panels. Now, you need a lot of solar panels to produce a tremendous amount of power, and that's sort of an issue in that industry. Where are we going to put all these panels, all the space that they take up? I saved for third on my list the most common method of creating a potential difference. I have here this apparatus that it looks so old-timey, doesn't it? It looks very steampunk. That's because it is actually very old. It was made by a company called Sergeant Welch at a time where there was very little plastic. The light bulb socket is actually plastic, but at the time this was made, plastics were a rare and new material, and now so many things in our lives are made of plastic, and often we lament that things that are made out of plastic have kind of a cheap feel to it. No, this is steel and brass and wood, a magnificent old device that still works extraordinarily well. If you don't appreciate the science of it, it seems very magical. It has a crank handle on it here, and I turn the crank handle and the light bulb lights up. I think we know, without me having yet gone into any detail, that in order for the light bulb to light up, there needs to be some potential difference. You need a voltage. You know very well that in your house, all of the lights work because there's a voltage, because you pay your electric bill. But here I get busy cranking the thing, and it creates a voltage that lights the light bulb. I know that there's energy there because there's energy associated with the behavior of the charges, and there's energy associated with the light. It's a wonderful thing that's going on. And it turns out that if I have enough strength and endurance, I can create quite a bit of potential difference and create large electrical effects. What's going on inside of the apparatus? Here you see there are three sort of bent metal bits here. They kind of look like magnets. It's because they are magnets. Three horseshoe magnets lined up like this. And in between the tines of the magnets is a coil of wire that I use the crank handle to rotate that coil of wire in the magnetism created by the magnets. It turns out that when you rotate a coil of wire in a magnetic field, it creates a potential difference in the coil of wire. Now, there are lots of details to that, and unfortunately in our course we won't have time to get into those details. They're really impressive. But this phenomenon is called electromagnetic induction. On the slide I've called EM induction just to save space, but it's electromagnetic induction. It's the interaction between the electrical effect and the magnetic effect, and it creates a potential difference. This is far and away the number one method that human beings use for creating potential difference. Oh no, Shadi, you forgot about nuclear power. We use a nuclear power plant to create electricity. Well, what's happening there is that in a nuclear power plant, a nuclear reaction is allowed to proceed, which produces heat. That heat boils water. The water is then steam, which exerts steam pressure, which turns a turbine, which is connected to a coil of wire, which rotates in a magnetic field. It's the same thing. No, Shadi, I meant hydroelectric dam. Sure, you dam up a river, and now you allow the water to pass through the dam and out the bottom, losing its gravitational potential energy and generating electricity. Well, that water is allowed to flow over a turbine, which turns a shaft which is connected to a coil of wire, which rotates in a magnetic field. It's the same thing. Oh no, but with the old school power plants, they just shovel the coal in there. Yeah, the coal is burned to heat water to create steam to turn a turbine, which rotates a coil of wire in a magnetic field. It's the same thing. Yeah, but you left wind turbines off the list. Yeah, the wind blows and turns the blades on the turbine, which turns a shaft which has coils of wire in it that rotates in a magnetic field. With the exception of the photoelectric effect and the chemical reactions that take place in batteries, almost all of our electrical potential difference is created by electromagnetic induction, rotating a loop of wire inside of a magnetic field. Here once again I see this diagram that I'm getting a lot of distance out of, where I have a potential difference and the potential difference causes a flow. We refer to that flow in electricity as current. And you see how pervasive this water analogy is. I go down to the side of the river and I can see, due to visual cues of the surface of the water, maybe some things, there's a duck floating, I see that the water flows by. We call the flow of water in a river current. And I'm going to do the same thing for electricity, except it's not water that flows, it's electric charge. The potential difference pushes charges to move. When they move, we call it current. Here, the potential difference gravitationally creates a flow. The potential difference in electricity creates an electric field that causes the flow. It's not gravitational, it's electrical. And that produces a little bit of a wrinkle that I need to mention. In wires that carry electrical current, it is the electrons that move. And we've already discussed this before because I advised you that anytime you observe electrical phenomenon, it's probably the electrons that moved because electrons have such a very small mass. Protons are big and fat. So anytime there's electric fields or electric potential difference, they're simply related to each other, that would cause charges to move, it's the electrons that do the moving. Here, I have drawn in this very, very simplified diagram. It's not very physically realistic. It actually just shows the relationships. If I have a place where the electric potential is high, here on the left-hand side of my diagram, and I have another place where the electric potential is low, I'm not explaining to you how that happened, I'm just asking you to accept it as a fact, then the electric field points from left to right. The electric field points from high to low, the same way the river flows, from high to low. It's a very sensible thing to do. The trouble is that whereas I've already made it very clear that positive charges feel a force in the direction of the field, negative charges feel a force opposite the direction of the field. So my potential is going from high to low on my diagram from left to right, but the electrons go the opposite way. In a previous lesson, I made a quip that if there were negative mass, the negative mass would roll uphill. Well, that's what's happening here. If you think of current as electrons, the electrons are rolling uphill, and that offends my sensibility. First, let's figure out who's to blame for this. Well, it's Ben Franklin. Ben Franklin made the choice that the resonance electrical effect would be called negative. He didn't know that electrons and protons existed. He didn't know anything about the fundamental charge. He might have speculated about it, but he didn't know. So he accidentally made the electrons negatively charged, and now I got to deal with it. Because if I say that it's the electrons that flow, all of my equations are going to have a negative sign in it. I don't like that. The way around it is that when we use electricity for our technology, we imagine that it's the positive charges that flow. This does no harm at all to the math because the positive charges and the negative charges have exactly the same quantity of charge, just opposite in sign. So it makes no difference to the physics if we choose to imagine that it's in fact the positive charges that flow from high to low, just like a river flows downhill from the mountains to the ocean. This choice that we make is known as the conventional current. Conventional because we've agreed to deliberately say a thing that is physically wrong. It's the negative charges that move, but we're going to imagine that it's the flow of positive charge, that it's the conventional current. So at this point, I understand the current in the context of it being a flow of charge. But if you're really paying attention, you know what happens next. I want a mathematical definition of the current. I want to be able to calculate it. So as I do, perhaps much to your chagrin, I convert it into an equation, my definition of current. First in words though, the electrical current is the rate at which charge carriers pass a point in space with respect to time. Words, 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 words. I wanted to be careful with my words, so it was very science-y. This is the equation. The current, which I'll give the symbol capital I, is equal to a certain delta Q, a change in charge, which is totally okay to think of that as the amount of charge that goes by. Just like if I were standing at the river and I imagined how much water goes by per second. The current, I, is the rate at which charge flows. It's not surprising that I would be using a rate here. I did it since the very early moments in our course, where I said that the velocity was the rate of change of position, and then said that the acceleration was the rate of change of the velocity. Rates are very useful quantities, and the current is a rate. Since it has the charge, Q, in the numerator, which is measured in coulombs, and it has the time, delta T, in the denominator, which is measured in seconds, then sensible SI units for current would be coulombs per second. That makes an awful lot of sense. But really, as a practical matter, that's not what we call it. The unit of electrical current is named after one of the famous physicists who was busy organizing all of these ideas for us around the late 1800s, Ampere. So the unit of electric current is sometimes expressed as amperes, but that's a lot, isn't it? And so we sometimes shorten it to amps. How many amps are running into that thing? An electrician might say. But amps plural, we don't usually express units that way. So you might say, just say amp. That is a 5 amp fuse. Would be a perfectly legitimate way of saying that. But ultimately, we use capital A as the official symbol for the ampere. So I might write that the current I is equal to 5A, 5 amps of electrical current. It's very difficult to get a sense of scale of these intangible, invisible things. I might look at a river after a heavy storm and see a torrent of water going by, and then I would have a sense that that current was dangerous. Just very quickly, because I know that there's a sort of inherent curiosity with this. How much current is actually dangerous to me? Because I know, I've heard rumors, that from time to time, a human being has a bit of misadventure with electricity that does not end well. A sustained current of 100 milliamps, that's 0.1 amps. A sustained current of 0.1 amps will kill you, no doubt about it. The thing is, you're not a conductor, so it's very difficult to push more than 1/10 of an amp of current through your body. It takes a high voltage, and it takes at least 50 volts. And even then, you need special conditions. In your house, you're sort of more or less safe when it comes to your household outlets, because they can't push enough current through your body to do any kind of real damage. But your dryer and some of the larger appliances in your house are connected to 250 volts. And despite the fact that you are a very poor conductor, the 250 volts is enough to push a large enough current through you to actually be lethal in those contexts. But in any given situation, there are often extenuating circumstances. It can be a bit difficult to work out. But a tiny bit of current can actually do a lot of harm. I mentioned in a previous discussion, I'm just realizing now, that if I take a balloon and I scrub it on my head and transfer electrons from my hair onto the balloon, I can charge that balloon up to 5,000 volts. Oh my gosh, Shidley, that balloon is dangerous. Well, it's not, because if I were to come up and touch you with the balloon and that charge was to shoot onto your body, it is very little charge for a very short period of time. It simply doesn't have time to do damage. When you're walking around your house and you experience like a touch the doorknob, snap, and you can actually see the light and you see the electric discharge, there's a spectacular amount of voltage there. If that spark is about 1 centimeter long, then the voltage is about 10,000 volts. The thing is, the spark is not a lot of current to begin with, but it's so short in duration that it can't really do any damage. It could burn a few skin cells on the tip of your finger, but there's not enough energy there to do it. In order for there to be danger, that current would have to be sustained. So I've got a potential difference, and a potential difference is going to make the charge flow. But the amps is something I can calculate. I could have a lot of amps or a little bit of amps. The current varies. What is the deciding factor? Well, if I have a potential difference and I'm going to allow charges to flow, those charges are going to flow through some kind of a medium. And different materials have different conductivity. We already mentioned that the rate at which charge can flow through a substance is limited by the conductivity of the material. Gold is very conductive. Rubber is almost not conductive at all. And everywhere in between. Copper is an excellent conductor. It's not as good as gold. So there's a whole spectrum. I look up in a book or look up on the internet the values of conductivity. Well, the way that we go about it, the way that we view it, is not the conductivity, but the inverse of the conductivity, the resistivity. The resistivity describes how resistive a material is to the flow of charge. I mentioned that you, as a human being, have a high resistivity. It's not easy to make charge flow through you. Gold has a very low resistivity. It's easy to make charges move through gold. So I invent a quantity, a numerical quantity that's going to represent that. It's called the resistance. Notice on my slide, I put an arrow here, not an equality. Scientists who study the behavior of materials and investigate the forces and interactions that create the resistance of materials to the flow of charge might be able to give you an equation that would allow you to calculate how resistive various materials are. We're not going to look at it that deeply. We're simply going to say that every material has some resistance associated with it. The SI units of resistance are the joules second per coulomb squared. Okay, now things are getting weird. But that's not surprising because our physics keeps getting more and more sophisticated as we go, and we're encountering now quantities that are more abstract, and their SI units may sometimes be a bit dense and difficult to interpret. The joules second per coulomb squared, let's not worry about it. Let's use the name of the physicist who was, I guess, sort of awarded with this unit. The unit of resistance, the ohm of resistance. The symbol for the ohm, and I know you just can't get enough of these Greek letters, is the capital Greek letter omega, is the unit ohm, which is the resistance. The resistance is the opposition to the flow of electric charges. If I increase the voltage, I will increase the current, because by increasing the voltage, I'm increasing the push. If I decrease the resistance, I will increase the current, because by decreasing the resistance, I am more welcoming to the flow of positive charges. I can't help but feel that there's a mathematical relationship in there that connects voltage, current, and resistance, and that is the subject of our next lesson.